So what can we do with the equilibrium constant? Let's take a look at how stoichiometry affects the equilibrium constant, reversing reactions, and what about Hess's law? You could quite easily write an equilibrium expression for this reaction at this point. I would assume you could write this. And if we reverse this reaction, you would write this, right side over left side. If you compare these two, you can notice that this second reaction is the inverse. So the punchline is here that when we reverse a reaction, we will take the inverse of the K value. Let's contrast that to what we were doing for G, S, H, and E, in which when we reversed a reaction, we changed the sign. We will not change the sign of the equilibrium constant. We instead will take the inverse when we reverse a reaction. What about if we change the stoichiometry? Same reaction here, we could write an equilibrium expression. What if we double the stoichiometry of the reaction? You would rewrite the equilibrium expression with those new stoichiometry values, which this you could, of course, pull out the square. And here's the punchline. When we double, we would square the equilibrium constant. Or in other words, when the coefficients are changed by some factor, say n, the equilibrium constant is raised to that same nth factor. Unlike G, S, and H, in which we would multiply by that factor, here we must raise to that factor for the equilibrium constant. And remember that E, when we change the stoichiometry, does not change at all. What about Hess's law? When using Hess's law and the reactions are added up, as we do, the equilibrium values are multiplied, not added the way we do for S, G, H, and E, multiplied for our equilibrium constants. The explanation is here. It's incredibly long and drawn out. If you want to look at it, you can check it out in the packet, the presentation packet that you can find on Google Classroom. So let's take a look. And notice that if we happen to know the equilibrium constant for this reaction, AP could say, well, what is it for this one and what is it for that one? Pause the video and take a look. And so you can see that this A reaction is the reverse of this reaction up above. So of course we are inversing the K value. You can see that this second reaction is 1/2 of the stoichiometry of the top reaction. So we would raise the equilibrium constant to the 1/2 power, that is to say, square root. Now here comes a Hess's law. So pause the video, give this a try, write this reaction down below, and build that reaction with these, and apply the appropriate conditions to the K. You can see that in order to build this reaction at the bottom, we need to multiply the top reaction times 2 so that we can end up with 2 NOBR. That will mean that we'll square the equilibrium constant. You can see that the second reaction needs to be reversed so that the N2 and O2 will end up on the left-hand side and be part of our reactants. And so that means that we will inverse the equilibrium. You could do this without a calculator. Certainly you can square 4 and get 16. And certainly you can write down the inverse of 2 times 10 to the minus 30th. 16 divided by 2 is, of course, 8. And 10 to the 30th in the denominator is the same as 10 to the minus 30th. This is the kind of question you could be asked to do in a multiple choice. Let's remember that no solids or liquids in the equilibrium expression, only gases, only aqueous. We saw that when we were discussing Q earlier. You may be asked, however, to watch out for that. We have to pay close attention, pause the video, and see if you can write the equilibrium expression for these 3 reactions. Hopefully you notice that you should leave water out of this expression. It's not in the denominator because it's a pure liquid. With the second one, hopefully you notice that 2 of the chemicals are solids, and so only the gas, of course raised to the power of 3, will be in the equilibrium expression. If this reaction had been written backwards, the equilibrium expression would look like this. So this reaction, which involves solids, aqueous, and gases, we have to mix, and so this is a true heterogeneous reaction in which we have the concentration of some of the chemicals and we would involve the pressure of the other. You're not likely to see this in an AP question, but it's certainly not out of bounds. And now let's do some calculating of the equilibrium constants. We can only hope AP would give us a problem as easy as this. Pause, and without your calculator, go ahead and see if you can compute the equilibrium constant. And coming in with the values, you can see pretty quickly that these are pretty easy to do without a calculator. 12 squared, and so we have a 12 down below. We can cancel one of them, ending up with 12. We could only be so lucky and hope to get a question like this, but it's not usually what you see where they'll give you values and you're just plugging and chugging. Instead, we're more likely to see something like this. Ammonia is placed in an empty flask at 3 atmospheres, allowed to decompose into its elemental gases. At equilibrium, the partial pressure of nitrogen is 0.25. And they're asking you to calculate the equilibrium constant. First, we'd write an equation, which from the words up above here, you could be expected to write. Then we need to turn that equation into an equilibrium expression. And now we want to build ourselves a rice box. So we have that here, and we want to plug some information. We've got our reaction in the first row, and then we want to put some initial information in. This, of course, is information as well. And so we should end up with 3. An empty flask tells us 0 of each of these. And then, of course, we've got some information at equilibrium. We've got 0.25 of the N2, 0.25. That, of course, gives us information that we must have formed 0.25 of this nitrogen. And then, of course, because of the 3-to-1 ratio, we can say between nitrogen and hydrogen, we can say that this must be 0.75 at equilibrium. And of course, now because we have a 2-to-1 ratio, we can multiply by 2 over 1 and realize that we must be losing 0.5, which of course allows us to finish with 2.5. And then we can go ahead and calculate equilibrium, which isn't really the issue. The issue is, are we able to take information out of this problem, fill out our rice table, and then, of course, go ahead and calculate. Next, I want to take a look at, don't want to be tripped up by the language, so we want to take a look at what AP will sometimes do and say, hey, we've got some 0.5 of some chemical initially, and after equilibrium is reached, 30% of that molecule remains in the flask. Well, that's pretty easy calculation. At equilibrium, we would be left with 0.15, 30% of the 0.5. But other times they may say, okay, we start with 0.8. This time I gave mole and a volume, which we can calculate a molarity from. And you're told 40% of the molecule has reacted. That's distinctly different from what remains as opposed to what has reacted. So we can take this 40%, change it to 60% is what would remain if 40% reacts. Change that, divide by the, do that calculation, divide by the volume, and end up with a molarity that we get at equilibrium. Then we might get a problem like this. We have 4 moles of NO2 in a 1 liter container. That's the same as 4 molarity. And 25% of NO2 remains, and the rest dissociating into NO and N2. Problem could read like this. What if 75% of the chemical dissociates? That's the same as 25% remaining. We just want to be careful with the language. Write a balanced equation. This information in the problem to help us with that. Write an equilibrium expression. And now let's set up a rice box to organize the information. So 75% reacting, which then would mean, because of the 2-to-2 ratio, we would be gaining 3 of this chemical, the NO, and because of the 1-to-2 ratio, we would be gaining 1.5 of the O2, which means 1.5 at equilibrium, 3 at equilibrium, and of course 1 at equilibrium, which we could plug in and end up with an equilibrium constant. Now let's talk about the reaction quotient Q, which we have used already. When you're given values that may not be at equilibrium, you can substitute those initial values into the equilibrium expression, call it Q, and if Q equals K, then you say, oh, we must already be at equilibrium. But if Q does not equal K, the reaction is going to shift either left or right. So let's try this problem. Here's a reaction telling you what K is, again, temperature, which we don't really care about, but we've got a K value and we have some initial values. Plug those initial values in and see if you're at equilibrium, and if not, are we going to need to shift to the right, or if not, are we going to have to shift to the left? Pause the video and try that. When you come on back, you'll find out that Q, which I don't want to call K because it doesn't equal K, so my Q, 2.5, is bigger than my K value. Thus, the reaction must proceed to the left so as to make the Q get smaller to be able to reach K. Also, if you line K and Q values up alphabetically, K first, Q second, the greater than or less than symbol will always point in the direction of the shift of the reaction. Okay, so here's the punchline. When you're given initial values and you plug them into your equilibrium expression, if the Q calculated equals K, then you know you're at equilibrium. If Q is smaller than the K, then we know that the right side is too small and the system will have to shift to the right to reach equilibrium. If Q calculates bigger than the equilibrium constant, we know that the right side is too large and the equilibrium will shift to the left in order to reach equilibrium.